Okay, so I'm not seeing anything on the forum. There's no specific questions there. So I think what I might do is, I think I'm just going to go ahead and start covering power factor, because it's going to come up a bunch of times in the upcoming lectures. So power factor is something we're going to see for week 5. So let me just go ahead and knock that out right now. So give me one quick sec to find those notes. I figure I'd rather just get a little bit ahead, and as questions come in for week 3 and 4, I'll answer those. But let's just look at power factor right now. Okay, so what I'm going to show you here, I'm just going to minimize as much as I can the reference to the company that contracted this, but I'll just focus on the physics. So there are a couple different, well, there's several companies out there that provide what's called a power conditioning device. And the purpose of the power conditioning device is to increase the power factor of an AC load. So let's go ahead and look at that. And what we're trying to reduce is this thing called kVAR. And so this is 1,000, that's volts, that's amps, and that's reactive. And I'll explain to you exactly what that means. We're going to see kVAR a lot when we talk about power factor. Now, I'm also mentioning in this little write-up that money is involved. That's the whole point of this exercise, to show that if you have a poor power factor, and if the utility charges you for a poor power factor, by putting a power conditioning device on your house, shop, building, whatever, you can save money. And so again, every single one of these problems comes down to, do I spend it now and buy the power conditioning device, or do I spend it later on the penalties for a poor power factor? So again, same exact question. So then I do a little bit of a quantitative analysis, say, gosh, you could save $200 a year, or as much as $1,600, depending on the size of your bill. So if you're paying 10 grand, you might save a couple hundred grand, you might save 1,000. So you're like, is the payback worth it? Maybe, maybe not. It's up to the buyer to decide. Okay, so what I do, I start this out with just kind of a little bit of a physics and mechanics lesson. Okay, so you've probably seen some of this before. We talk about our rate of energy consumption. And this is the company I was working with, Power CEO, and they're doing a neat job. So another disclaimer: this is not an endorsement or an indictment of Power CEO. They're out there, and there are other companies as well. And with any luck, they might be bought up by Westinghouse or whomever. So I'm not gonna. Nothing that I'm showing you here is giving away any of their trade secrets. Just want to make that clear that I'm not violating that. So the 3 things that we're going to look at are the true power, that's P, the reactive power, that's the one that I just mentioned, the kVAR, the reactive, so the R is coming from kVAR, and the apparent power, S. It's almost QRS, but it's not, it's PQS. It's almost alphabetical. So here's power factor, which we're going to measure and state. Here's the kVAR, or the reactive power, and here's kVA, which is just kilovolt amps.
Just kilowatts?
It's not well, it is kilowatts, but it's apparent kilowatts.
Okay.
It's apparent kilowatts. And I'll explain exactly what I mean by that in a second. Apparent kilowatts. Okay, so any electrical load can be a resistor, or a capacitor, or an inductor. or some combination thereof. There's, okay, well, there's diodes, and there's amplifiers and all that, but fundamentally, the only three types of loads in any system are resistors, inductors, and capacitors. That's just the physics and the reality. So what we see here is a LRC circuit. LRC. L is inductance, R is resistance, C is capacitance. And there's a few neat little online tools. So Falstead.com, Circuit LRC allows you to play with this. So you can sort of ramp up the inductance, ramp up the capacitance, and look at the lead versus the lag. The lead versus the lag. So think of the capacitor as sort of an electron bucket, and think of the inductor as just a river or a tube or a hose that electricity flows through, and the resistor is something that actually does work for you. So you can imagine electrons just sort of sloshing between these two, capacitor, inductor, capacitor, inductor, capacitor. Are you doing any work? No, you're just sloshing it around. So basically, any of this sloshing is what's called apparent power. Like it looks like you're doing something, but you're not. You're just sloshing electrons back and forth between capacitors and inductors. Well, here's the secret behind the power conditioners. The power conditioners are capacitors. Capacitors that are designed to match the inductive load. Because here's the deal. When you go to turn on the dryer, which has a motor in it, or the fridge comes on, or the washing machine, anything with a lot of coils in it, and any motor has, I don't want to say miles, maybe in some cases miles, but many, many feet of copper wire inside. So think of that as this giant garden hose or siphon that's sort of turned on, and when you turn it off, they're still sloshing around. Where do they go? Well, the load's turned off, so they just slosh back out onto the grid. So it's apparent power, but you didn't use it. You still paid for it, though. So it's that sloshing, or that's sometimes called dirty power, that the power factor device is looking to clean up. It can also be, I'm over here typing on my laptop, and here come all these big sloshy loads from the microwave and from all these things with motors and very large inductive loads. Well, it messes with other electronics.
Yeah, they call it noise.
Noise, exactly, yeah.
Frequencies.
Right. Okay, so that's the fundamental circuit, and hopefully that's the motivation for putting the capacitor on it. It's a damper. It's in order to dampen all that sloshing through the inductors. Okay, there's a few other tutorials out there. This is an LRC. What we saw a second ago was a parallel circuit. Now we're looking at series. So the capacitor and the inductor are now in series. The math is a little bit different. We do not need to go into all of the math for now, but we can just sort of categorize circuits by here's LRC, exactly in series, all three of them. Here's all three of them exactly in parallel. Here's your capacitor in parallel with your inductor. Here's your capacitor in series with your conductor. And here's these two guys are in, you've just sort of flip-flopped B and C. The inductor and the capacitor have swapped places. And beyond that, I don't think there's really any other fundamental way to arrange them. Okay, so you've seen this before. That's how you add voltages in series. This is how voltages look in parallel. Right? Okay, and what I tried to do here, this was kind of an artistic attempt to show a water analogy. So the capacitors are just buckets of water. The inductor is sort of a tube, and the whole thing is sort of sitting on a balance or a scale. So if I were to fill this bucket up, this side would go down, the fluid would run in here. If I then filled this guy up, it would slosh back and forth. But it's also showing that the system itself, it can't react immediately. So if I had, if I've got a resistor or a light bulb, the electrons go through, the heat and the light comes off, end of story. In this system, you can see it takes a while. It's got a time constant to it, sort of sloshing back and forth, and you might put the water in now, but okay, it takes a little while for it to move, then you take it out. So there's this sort of mass that's moving through, and the electricity you can think of as just the mass. Okay, now this is one of the figures that I'm most proud of, because what I've tried to do is show a purely mechanical system and a purely electrical system side by side. And this is my own creation, own invention, very proud of it, never seen it before, but I went out, I'm like, how does the electrical system in your house compare, or how's it an analogy to a mechanical system? Okay, so what's the goal up here? Is the guy going for a horse ride? No. Is the guy having a joyride on his gadget? No. The goal is to plow the field. I need to plow the field so I can plant the crops or whatever I'm going to do with it. So this is the goal down here. This is the actual work that's being done. But at the end of the day, you look, what'd you do? Well, I plowed the field. Oh yeah, sure, I rode the horse around a little bit too, but the riding of the horse, the movement of the horse is sort of the virtual work. Now we've also spent a lot of time in 101 and 102 talking about efficiency. So this system, so if I was going to go out and race somebody, I've got my field, the farmer next door has his field, and we're both racing so we can get the crops in, get home for dinner, whatever the competition has to be. You can imagine there are some good ways and some bad ways to design the system, right? So would I put would I make this thing all floppy and weird? No. You want a nice, stiff connection there. Would I tie these loosely onto my horses so it's rubbing? No. You want a nice tight connection. This guy too, you can see maybe he's got a little seat here, something, but sure beats doing it by yourself, right? So you got the horses doing the work for you. Nevertheless, the man is sitting here. The man has mass. The man has a certain body weight. And I don't, let's see, I think I've sort of obscured it, but I think there's a little tether here between the man and the top of the horses. If not, you can just sort of think of this whole system that he's riding on as a little bit of a spring. So in the mechanical system, you have the mass and the spring. M for mass, K for spring constant. So all he's doing, the man is just there, basically just bobbing up and down like a yo-yo. And despite how much bobbing around he does, it's not getting the field plowed.
Right.
That is apparent power. That is VA. Because where's the V? Well, the V is his mass times gravity. That's the force. Where's the A? Well, that's him moving back and forth. So the current is this guy bobbing back and forth. Why are you so tired? You didn't even plow the field. Well, the horses did the work, and I was just getting bobbed back and forth. Yeah, right. So this is apparent power, and it's and so you could think. You could even think of like, hey, I'm going to pay someone to do this. Well, if I design this wrong, and this guy's getting jockeyed around, I'm still paying for it because I'm paying for my poor worker to be out there in the field getting thrashed. So there's your apparent power. There's a lot of words. Now, down here, this is the real power. That's the real work that gets done. The field got plowed. Yeah. So there's your apparent, there's your real, this is your reactive. This is your reactive power. Because the horses are here too, and the horses really are just trying to push the plow or pull the plow forward. That's really all they're going to do. But there's still this up and down, because they're gonna feel the weight and the torque and this guy pulling on them, and that's their, I was trying to make a hand puppet. You know, that's what the horses feel in terms of, hey, we're not quite in sync here, quit bouncing around back there. So that's the reactive power. It's the horses sort of reacting to this apparent power. Why do I have this guy? Let's just plow the dang field. So as it turns out, lucky for us, these three types of power, real, apparent, and reactive, have a tidy little mathematical relationship, and it's just the Pythagorean theorem. So real powered squared plus reactive powered squared equals apparent power squared. We will use that in class. We will definitely use that in class. Yeah, Pythagorean theorem. So all that trig is going to pay off soon. And then let's get in a little deeper here. It was my goal to describe power factor to you, and these are the differential equations that govern. Kind of fun. Just sines and cosines. Get a little bit of trig. Nothing too crazy. And these guys are showing, so if you have a purely resistive element, so again, no farmer, the volts and the amps are exactly in phase. Exactly in phase. If you have a inductive circuit, the current lags the voltage. So remember, it's the voltage in the circuit, it's the voltage at the wall that's pushing it. Well, here I am, voltage coming up. Oh, current, what's taking you so long? Well, I was still filling the hose. I was still filling the garden hose with the water. That's why it took me a while to get all the way up. Well, now we've changed direction. Current, what's taking you? Well, I was emptying the hose. Fill it, empty, fill, empty, that rocking back and forth. Same thing down here. The capacitive circuit leads the voltage. So as the volts are mounting, the capacitor's like, hey, I'm already way ahead of you out here. I've filled up. So the capacitor is always like, give me those electrons. Boom, right now. Boom, right, sucking them right in. Well, the volts say, hey, we'll turn around. Okay, well now we've already emptied too. By the time everything's moving the circuit, the capacitor's already kind of done its thing. Right. Okay, so you get those analogies. Yeah. So, neat little gadget. Put a clamp on there to measure amps. That's an amp clamp right there on the house. So in the house you have 3 legs. You've got your neutral line, then you've got your pair of 120s, gives you 240, A and a B leg. Yep, exactly. So measuring both of those, because half the circuits are on one, half the circuits are on the other, typically. Yeah. So there's my little setup. There's their gadget. Oh yeah, this is all kinds of fun. And this is showing the results. So here's the juice coming in. Here's the results coming out of the gadget, doing its thing. A lot of different harmonics come on. This is showing in and out of phase. And so this guy right here is the power factor. And let me go out. I'm just going to dive out online really quickly here. Just grab that for us. Okay, So the power factor is just equal to the true power divided by the apparent power. So it's the bottom line divided by the hypotenuse.
Okay,
So it's the long, usually the long line on the bottom,
the base.
the base divided by the hypotenuse. It's that simple. It's those two numbers. So if you are able to, flatten that, where you have no reactive power, they're equal, and your power factor equals 1, because the hypotenuse equals the base. Pretty simple. So in this case, we can see that the power factor was relatively low. As soon as I turned it on, hey, look at that. Power factor increased, so I turned on the capacitor bank. Didn't change a lot, went from 96% up to 99%, but 3% is better than nothing, right? Okay. So let's see if there's anything else. So we're showing the phase. The phase is coming, back in when the thing comes online. That's what you want. Remember, we actually want to get back into phase. We want to be here. This is what we're aiming for. Oh yeah, go for it. This is what we're aiming for. And so, I guess the conclusion, the easy thing to reach, to show here is that power conditioning factors work. Will it save you money in every market? Not necessarily. Depends on your local utility rates, but there they are. So what we'll see down the road in ETEC 214 is that there will actually be there'll be demand charges. So when your rate of power consumption goes up, there'll be a charge for that. And you'll also see that when you have a poor power factor, the rates also can go up as well. So what we'll see moving forward, there will be if statements as well. If the power goes above a certain amount, we're going to pay for it. If the power factor goes below a certain amount, we're going to pay for it. Same thing as a consideration. When we go and turn on the lights at the football stadium, for example. Big demand charge coming in from that.
That's a lot of power needed.
Yeah, I wish I could remember, but it's I don't know if it's on the order of a megawatt, but I would say 50, maybe 100 kilowatts of power to run those lights. So, well, I wanted to cover that. It's something that we'll see, and we'll have to actually calculate the power factor a couple of times, based on what we see for reactive power and apparent power in the course. So there you go. I think we're kind of a week ahead, and I look forward to everybody's comments during week 4. So thanks a lot.
Stay ahead, I'll stay on target.
Perfect.